Welcome to video 7 of the regression analysis course. So far, we have seen that when we only have the dependent variable and no independent variables, our model looks like this. Yi is equals to beta naught plus epsilon I. For I is equals to 1 to n, where this I represents the number of observations. So in this case, we have n number of observations. If we look at this model equation closely, we have only one parameter present in the model, and that is beta naught. And this beta naught is an unknown fixed quantity. And the other term we have in the model equation is the error term from the ith observation. This beta naught is the parameter we have in the model, and this EI is the uncertainty we have in the model. Now the big question is, how do we estimate this beta naught in a way that the overall error is as small as possible? We want this epsilon I to have a very, very small value. And for that, we'll use something called the ordinary least squares method, or OLS. What's the idea behind OLS? It's simple. We basically want to minimize the sum of squared errors. And I introduced this method in the last video. Remember, in the last video, we saw this intuitively that if we have a bunch of values for the dependent variable, then the best prediction we can make is just the average of all those observed values. Why average? Because that average is the one value that's kind of in the middle. It's the closest overall to all the other data points. But that was our guess, our intuition. In today's video, we will prove this mathematically. Given a dependent variable and no other information, we have a null model equation yi is equals to beta naught plus epsilon I. Now what we want is an estimate of beta naught using OLS method. That is an estimate of beta naught by minimizing the sum of squared error. Now when we say sum of squared error, it means that we have an error term from each observation. That is, we have EI, we square it, and therefore we have squared error from each observation. We take the sum over n number of observations and find its minimum value. Now, when we are finding the minimum of this function, the goal is to have an estimate of beta naught. Perfect. So we want to have an estimate of beta naught by minimizing the sum of squared error. And now to find the minimum of this function, we'll use some basic calculus. Suppose you have a function y is equals to f of x. Now to find the value of x, where the function is either at its minimum or maximum, here's what we do. The first step is to take the first derivative of the function f. The second step is to set this first derivative equals to 0. And the moment we set this derivative equals to 0, it gives us critical points. Now to find out if the function takes the maximum or minimum value at that critical point, we take the second derivative of the function f and plug in the critical point. If the second derivative is positive, the function is curving upwards and it's a minimum value. And if the second derivative is negative, the function is curving downwards and the function f takes the maximum value. Perfect. So this is all what we need to know in order to estimate beta naught. We minimize the sum of squared error, and this method is called ordinary least square estimation method. What are we doing? We are finding an estimate of beta naught that minimizes the sum of squared error. We are estimating beta naught that minimizes this function. So we are minimizing the function summation I going from 1 to n epsilon I square, and let's call it s. S is just a notation we have given it to this function. Given only the dependent variable, no features, no predictors, we have this null model equation. And what we are interested in is minimizing this function s to estimate beta naught. But wait, here's the thing. Do we know epsilon I? Epsilon I is the uncertainty we have in the model. And we have no idea about this error term. So, how do we find the minimum of some function if we don't really know anything about that function? But the catch is, we know the null model equation. It is yi is equals to beta naught plus epsilon I. And from here, we have that epsilon I is equals to yi minus beta naught. So when we say we want to have an estimate of beta naught that minimizes the sum of squared error and we do not know that epsilon I, that error term, we can use this model equation and put this epsilon I is equals to yi minus beta naught. And the moment we put this epsilon I is equals to yi minus beta naught in this function s, we get S is equals to summation I going from 1 to n yi minus beta naught whole square. And if we look at this equation now, for each observation 1 to n, we will have the value of yi. And we will minimize this function S over beta naught. And we will use basic calculus in it. We have this function S, we take the first derivative of this function S with respect to beta naught, and get this result. Here we have used the chain rule, and the derivative of summation I going from 1 to n yi minus beta naught whole square would be negative 2 summation I going from 1 to n yi minus beta naught. The second step is to set this first derivative equals to 0. If we do that, we get negative 2 summation I going from 1 to n yi minus beta naught equals to 0. And now we need to solve this equation for beta naught. What we have is negative 2 summation I going from 1 to n yi minus beta naught equals to 0. The first thing we'll do is we'll use the 0 property. It says that if you have two terms a and b and a times b is equals to 0, then either b is 0 or just a is 0 or both the terms a and b are 0. Now if we look at this equation closely, we have negative 2. Negative 2 is not equals to 0, which clearly implies that summation I going from 1 to n yi minus beta naught will be equals to 0. So now we need to solve this equation for beta naught. We'll distribute the summation sign on both the terms and we get summation I going from 1 to n yi minus summation I going from 1 to n beta naught. What do we do next? If we look at the first term, we have summation I going from 1 to n yi. In the null model, we have only dependent variables. So for all the observations 1 to n, we will have the value of the dependent variable. We would have y1, we would have y2, we would have y3, so on and so forth till yn. And if we add these observations from 1 to n and divide it by n, we get the average of this variable. And if we multiply this n both the sides, we have summation I going from 1 to n yi is equals to ny bar. Second term we have in the equation is of beta naught. What we know about beta naught is that beta naught is an unknown quantity, but once we estimate its value, it will be a fixed value. It's not going to change as you move from one observation to other. It will be a fixed quantity. It is unknown at this moment. Once you have the value, it will be a fixed quantity. So if you take the summation of a fixed quantity from 1 to n, you just get n times that quantity. So from here, we have that summation I going from 1 to n beta naught is equals to n beta naught. Thus, the first term, summation I going from 1 to n yi, would become ny bar, and the second term, summation I going from 1 to n, would become n beta naught equals to 0. Now be focused because I'm going to talk about something most of the people get confused with. When we talk about the null model equation yi is equals to beta naught plus epsilon I, here beta naught is the true value of the parameter in the population. And it is unknown to us. We don't know what it actually is. It is unobserved, but it exists out there in theory. So what we can do is use the data we have and apply some method. Here we are using ordinary least square estimation method to get an estimate of this unknown value beta naught. And once we have calculated that estimate from our sample, we give it a special notation beta naught hat. So the little hat we have over here over the estimate, that means that it's an estimate of the parameter. So just to be clear, this beta naught is the unknown population parameter and this beta naught hat is the estimated value of beta naught based on the sample data. So what we are doing over here is we are minimizing the sum of squared error to get an estimate of beta naught. This beta naught is unknown. We want to find a value for this beta naught. We want to find an estimate of this beta naught, which means that when we solve this equation and get an estimate of this beta naught, we'll just give it a notation beta naught hat. Reason because we are assuming that beta naught is unknown, and whenever we say an estimate of beta naught, instead of writing its value, we can just say that it is beta naught hat. So beta naught hat is just a notation for the estimated value of beta naught. So in this equation, we have n y bar minus n beta naught equals to 0. We replace the beta naught by beta naught hat. And when we solve this equation, we get beta naught hat is equals to y bar. Therefore, using ordinary least square estimation method, we have an estimate of beta naught and it is equals to average of all the values of the dependent variable takes for each observation in the data set. Given a dependent variable and no other information, we have yi is equals to beta naught plus epsilon I for I going from 1 to n. We just saw using ordinary least square estimation method that an estimate of beta naught is equals to the average of the dependent variable. So we have an estimate for beta naught. But if I ask you all a question, what would be the best prediction for the null model? The answer would be the best prediction or estimate for a null model would simply be an estimate of beta naught, which is beta naught hat. And there would be no error term involved here because that's the best prediction we have based on the data. It's the value we are confident about. No confusion, no uncertainty, just the cleanest estimate one can get from the data. An estimate of beta naught we have using ordinary least square estimation method is the sample mean y bar, and thus, that becomes the best possible prediction the model can make given there is no other information or predictors available. In the last video, I said that the mean would be the best possible prediction we would have for any n plus observation. And here we have proved that sample mean is not just a guess, but it is for sure the best prediction the model can make.